All right, so I decided to re-record the lecture we had on Tuesday and Wednesday, um, the one that covered the sort of the basic sort of application of quantum mechanics to one-dimensional problems. Part of the reason for that is that I'm not sure how clear the Zoom recording is generally, because things are sort of real time and maybe rushed. Partly because I've always wanted to try this PowerPoint recording because it allows for small tweaking, and partly because we ran out of time and we didn't cover an important example which shows up in homework 6. So the plan is to go through the slides quickly. If we covered them before, the last 5 or 6 slides I will slow down and explain things. Okay, so as was announced, I think on Monday, in part because of some feedback I got from some of the students, I think it's pretty clear that I want to differentiate more between those of you who are signed up to take the basic quantum mechanics class versus the ones who've had it before and are here for the quantum computing component. And the way I'm going to differentiate that is record 2 sets of lectures and maybe play them in class and comment over them. But more importantly, there will be 2 sets of homeworks. So homework 5, which was assigned much earlier, is for Physics 443. It's optional for the ones who are signed up for Physics 442. Homework 6, which was assigned on Monday, and I guess we haven't fully decided when it's due, sometime this week, I mean, since it's been over a week, is for Physics 442 students. The most important thing is that we've decided, so there will be a guest lecture, and after consulting with some of you, those of you who responded at least, it seems that 9 a.m. on Friday is the optimal time. I would like to ask the rest of you to kind of try and make it. Okay, and without further ado, let's keep going. Okay. All right, so since you can read these comments yourself, I will just sort of quickly summarize these slides. Well, I already said what's on this slide, so let's keep going. So here's what I would consider the bare minimum of basic quantum mechanics that all undergraduate courses on quantum mechanics should cover. The axioms that we covered. There are 2 different kinds of single particle solutions, qualitatively different, bound states and unbound states. And for the quantum computing sort of applications, we're mostly interested in bound states, and that's what we've focused on, the qubits in particular. But both are important quite generally, and so they need to be understood. The bulk of the work in a sort of elementary quantum computing class stays in one dimension, where we work out different properties, different sort of general properties of quantum mechanics by using very special examples that are exactly soluble. And they're listed here. The only one we haven't covered that we will finish on Monday is the simple harmonic oscillator. All the rest of them we covered. And the homework 6 is essentially just working out some details of things that we already covered in class. So approximation tricks, I think, are very important because quantum mechanics earned its way into the canon of physics by solving things. It has deep philosophical implications that are still reverberating, but that's not that, the solving outstanding problems of the day is how it made its way into physics. And so to do so, one needs to do better than these simple toy problems in one dimension. One actually has to learn a set of ways to approximate when one cannot solve things exactly. Finally, there's a wealth of solutions in higher dimensions, but we'll touch on a couple of aspects of that. Mathematically, these are more challenging, and so one has to sort of take it at an appropriate pace. And finally, applications of quantum mechanics to identical particles and quantum statistics is the last required topic. Okay. I think I more or less said this. Right, so there is the important step of reducing the Schrodinger equation, which is highlighted here, to the so-called time-independent Schrodinger equation, which involves, well, actually, no, let me make one comment first. So the solutions of the Schrodinger equation can be roughly divided into those that have a spectral gap and those that are gapless. The ones that have a spectral gap is, well, as the name implies, two adjacent solutions are separated by a finite number. And well, as we'll see on some examples, there are cases where adjacent solutions are separated by a number which is vanishing in a precise sense. So a gap in the spectrum is detectable because what one expects is that if one excites the system by doing something, by changing some parameters, it'll ring, right? And the ringing frequency is typically obtained by looking at either the smallest gap, which is the adjacent two levels, or maybe n+2 minus en. In other words, there are finite energy differences will necessarily translate into finite frequencies at which the system rings afterward. And this is how quantum mechanics, as I already alluded to, initially earned its place by explaining lots and lots of spectroscopy data from atoms, for instance, and eventually molecules and so on. Okay, so in one dimension, we still have a significant challenge, which is, the space is infinite, so we have to think of infinite dimensional problems. And I apologize that my slides do not leave the little square here. I'm just realizing that this video recording has its own space needs. Anyway, so in one dimension, we basically are, in real physics, we're forced to think about infinite dimensional matrices. Okay. One can circumnavigate that by thinking mathematically of differential equations and operators. In fact, the early examples of the Schrodinger equation were essentially classical energy functionals that were quantized. And so if we think of a classical energy, it's the kinetic energy plus the potential energy. And as we know from elementary courses, physics 120, for instance, we can think of potential energy as just a function that goes up and down. The kinetic energy is p squared over 2m. It's basically some measure of the energy contained in the motion. And the idea now is that these objects can now be promoted to the status of operators. And what that means in practice is that, well, visually, we just put hats on. We'll say more about what x is an operator is. It's just x. It acts on functions by multiplying things by x. The momentum as an operator turns out to be the right choice as the derivative, and I can assign that as a homework problem to derive, but it would be a distraction now. It seems like elementary quantum mechanics books are split 50-50 on whether to introduce that at the outset, and so I'll just say that this is the answer. And therefore, the kinetic energy is actually the second derivative. And so with that in mind, what you can think of it as just a definition of what an operator is when it's acting on infinite dimensional sort of functions, functions that live in real space. Or you can think of it as a very large discrete matrix by imagining the real space is discretized, right? And then the derivative has a meaning, which is basically a difference between 2 points, as we you guys all learned in elementary calculus. That's also an interesting sort of a diversion to actually see how the different ways of discretizing space are equivalent when one thinks of it correctly. Anyhow, yeah, so this is one of the sort of descriptions of the position operator as an operator. Usually when we say x, we mean the eigenvalue of the operator, namely what is the distance or location of a given sort of a object. In this class, and certainly in elementary quantum mechanics, x can be used in 3 different ways: as an eigenvalue, as an eigenvector, and ultimately as an operator, which is a very non-classical object that basically lives everywhere in space. Okay, one of the important things is to think about, in thinking about these things, is matrices. As we learned a few weeks ago, matrices generally do not commute. And in particular, x and p that were defined on the previous slide, you can just take them as functions and operate them on another function, and the ordering is important. Right? X would operate by multiplying things by x, p would be a derivative, and you can see that the order of when you take x and multiply it by a function, so x derivative with respect to x gives you a different result than otherwise, and you know this because you know that there's a derivative, there's a multiplication formula for derivatives. You can derive this commutator that way. So the time-independent Schrodinger equation is basically when you take your initial state to be just an eigenstate, and then what you will have is the only time dependence will be just as oscillatory phase. And so the whole problem of solving the Schrodinger equation reduces to solving for this equation that has no time in it. And as we quickly sort of saw in class, the magic here is that the exponential functions are extremely friendly to derivatives. They are proportional to themselves, so the derivative just brings down en, and then everything just cancels off. Okay, so the example that we went through in detail, and I'm gonna just quickly flash the slides, is the time-independent Schrodinger equation for the an infinite square well, an infinite potential well, namely it's a well where outside of the well the potential is infinite, and therefore no particle with finite energy can penetrate there. And inside the well there's no potential, so it's just kinetic energy alone determines things. Okay. So since the wave function is the probability of having a particle outside, the fact that the particle cannot be outside because of the infinity of the potential means the wave function has to vanish. Okay. And as we'll derive later, the wave function has to be continuous, and therefore the solutions that you expect they look like vibrating guitar strings. Right? Basically, just like outside everything is pinned down, and inside it just has sines and cosines. Now the crucial thing is that having a fixed size of the well known ahead of time means that your the spatial period of these vibrations is not arbitrary. It comes in as a discrete set. So the way we solve the Schrodinger equation in the absence of the potential energy, we just basically look at the second derivative and we ask what solutions are allowed, and they're either they're all exponentials, plus minus exponentials. And depending on whether the energy is positive or negative, the exponentials are either oscillatory exponentials, which is sines and cosines, or they're decaying exponentials, and we'll see both. So as long as the energy is positive in this well, we're going to be looking for oscillatory objects. And like I said, the potential being infinite outside of the well means the solutions vanish at the boundary. And that basically just guarantees for you that these are sines and cosines that appear in this pattern, but more importantly, or more simply, the k's that are allowed by this equation are very specific. They're basically kn equal pi over 2a times n, and that's just to make sure that you fit a whole number of half periods in there. Okay. And finally, this pattern of cosines and sines, I don't think I can back up on this slideshow anymore, implies that the coefficients a plus and a minus are basically plus minus 1. Sorry, the 1 is now blocked here. Okay, we went over this in class, so if you have any questions, you should ping me on Slack or whatnot, or bring them to class on Monday. The thing that's left over is normalization. That fixes the overall magnitude of a plus minus to be in absolute value 1 over root a. And putting all this together, we get, this is the outcome. This is the spectrum of the problem. These are the energies. These are the wave functions, the eigenfunctions. And you can see that the energies, because these are integers, the energies are all finite, and so the gap is finite. The gap is the difference between the energies. Now, we can now take this example and tweak it. In particular, if we let the size of the box increase, this box could be a model of a very large space, maybe even the universe. And so what you expect is that the spectrum should go gapless because the spacing appeared in the denominator. Okay. Right, just to illustrate this with an equation, this was the result for the spectrum there, and this is the result in empty space. You can see that, okay, this is, no rocket science to see how you can basically identify these things by saying that, okay, if I have a really big box, it's like having empty space with a particular, relationship between k and n. Okay. So the tricky thing, or at least tricky thing if you try to be very mathematical about it and stick to the original definitions, is what to do with the normalization, because normalization seems to be vanishing. And that's because, and the physics way of not worrying about it, but one can also make things mathematically precise, is to say that, look, this is single particle quantum mechanics. If the box is very big, we're talking about one particle being smeared over a very large amount of space. In reality, we're actually more interested in having a bunch of particles inside the box. This is why the quantum statistics might become important, but in some cases, in many cases, the results that we expect will be proportional to the density of particles. And so the right way to normalize these things, once we're doing quantum mechanics for applications to real world, is you can normalize it not to be, you can normalize probability not to be 1, but being the total number of particles, which would be proportional to A, and that would remove this 1 over A. Okay, I think this is basically what's said on the slide. Now let's move on to a more interesting example, and that's the semi-infinite well. So we will keep the left side of this well infinite, so particles never leak into that, but now we'll bring the right side of the well from infinity to a finite number, V0. Now the important thing, and this is sort of this philosophy permeates all of physics. We want to hone our methods so they're more or less the same one problem to next. That way the steps are going to be the same. There may be extra steps if the problem is new and different, but we don't want to change the foundation, right? And so the foundation of the method is that, look, we have a partial differential equation, d2 by dx squared 5x is equal to e minus v of x phi, right? That's the partial differential equation. We just have to solve it. And so we just have to move to more complicated problems from simpler problems. And that just means that in this particular problem, the fact that the solution there's an infinity here, we're going to keep to this basis set, which is just sines, right? I've shifted the origin, so now all of the solutions that vanish here can be written as signs, because signs vanish at the origin. We will have to match the solutions at the boundary, but the solutions outside are going to be simple because the potential is constant. Right? The most important thing is that it has to vanish at infinity, because otherwise it's not going to get normalized if we're looking for bound states. Okay. So let's run through this. Right? This is the Schrodinger equation that I tried to narrate. As you can see, there are going to be two types of solutions. One solution is where the energy is bigger than V naught. In other words, if you consolidate all of the things that are basically that have no derivatives, right? If the energy is bigger than V naught, then we expect that the coefficients in the exponent are going to be complex, so they're going to be oscillatory exponents. If E is less than 0, then you expect that you can just put an exponential here and see what the equation for the thing in the exponent is. You can see that this is going to be it's called kappa because we see that when it's negative, it'll be a non-decaying, non-oscillatory exponent, but rather decaying exponent. And so you can see there are two types of solutions. And again, since we talked about it in class, let me just jump to pictures. So inside we're going to have signs, and outside it's going to be non-oscillatory exponents. The growing exponents are forbidden because they blow up and you cannot normalize them at all. The decaying exponents are what we expect to keep. So we can see now we need to count the things to match. So this is sort of the most general. So the infinite potential was sort of a warm-up example. So this business of matching matching solutions was not sort of fleshed out there, but now we're actually doing it. So you can see that there's a solution inside, which is has an amplitude A. There's a solution outside, which has an amplitude B. So A and B are not known. Kn for the inside is not known, and Kn for the outside is not known, but they're actually connected by the energy, because we have a formula for kappa n and Kn, and both of these formulae involve the energy, right? So in fact, we don't have 4 unknowns, we have 3 unknowns. We have A, B, and the energy, which is partially hiding behind my video. Okay, and so that's what we need to do. And so what are the, we have three unknowns. What are the equations? Well, one equation is always normalization for bound states, because it's about one particle. It has to be bound somewhere in space. That's equation number 1. The other 2 equations are going to be matching conditions. And the matching conditions, let me just rush ahead a bit. The matching conditions are that the derivative and the function itself, the wave function itself, are continuous across the boundary between 2 regions. And you can derive that essentially by taking the time-independent Schrodinger equation and integrating it near the boundary. I'll look at this comment. Okay, so at this point, here's an equation for which, here's an equation implementing the matching of the wave function. Here's an equation that implements the matching of the derivative. And of course, we have to match at the location of the jump, which I took to be A. And what you can see is that there are 2 equations. There's also an equation for normalization, which will help. But at this point, I just want to focus on figuring out the energy. And for the energy, we want to cancel out all of these A's and B's. We want to just go straight to the things that contain the energy and nothing else. And so the way to do that is to divide the 2 equations, you can see. And you can see that all of this then reduces to a simple looking equation that involves both a trig function, which is tangent, and a square root. And these equations generally don't have analytic solutions. And what we like to do is we like to convince ourselves that it's one of these kind of like general So problem solving skills is to first you want to convince yourself that the problem has a solution. How to actually get it may be difficult, but you don't want to invest all that effort until you convince yourself that the solution exists, right? And for these transcendental type looking equations, where here I reproduced it again, it's tangent of something is equal to a square root. The right way to do it is basically plot the two functions and convince yourself that they're intersections. Okay, so the square root of e divided by e minus v naught is a function that goes to 0 as e goes to 0. It's negative, there's a minus sign overall, so it's a negative square root down here, and it starts growing. It has a divergence when energy reaches v naught, and that we understood for physical reasons before, that there's a qualitative change in the solutions. So far we're only talking about bound states, right? So you can see that this function will start off here, go negative, stay negative, and then just blow up. It's a very simple function, right? It just does this. I just sketched it with by hand. Now, tangents are equally simple, and they have repetitive structure, right? And you can find where the zeros are by looking where, because it's sine by cosine, you just have to find where the sines is 0. And once you find where the zeros are, you also know where those blow up. And so you can draw this kind of like a little forest. It's because of the various square roots floating around, it's not going to be equidistant, but it's roughly speaking like that. And what you see is that because the first function is negative and tangents go negative and arbitrarily large, you guarantee that the two will intersect. Now, it's interesting that when v naught goes to infinity, right, which is the solution we used to work with, the fully infinite well, this whole curve gets squashed up and stretched out this way. And so that means that every single tangent, in other words, this red curve will, oh, I see, here I wrote v0 goes to infinity. That just means that it gets squashed up this way. So the location of the solutions is basically right where the tangent is 0, right? And so all that happens for finite v in this graphical representation is that this curve moves down. And so, first of all, these solutions are no longer right where the tangent is 0, but somewhere a little bit below. But the biggest change, of course, is that you no longer have an infinity of solutions. You just have this finite set. Okay. Now we went over what happens when the energy is positive. You basically have to match up plane waves. And the most crucial new aspect here was to note that there are too many unknowns. And the new aspect here is to realize that, wait a minute, there are different possibilities. It's like when you have a reflection-refraction problem, and of course, let's see if I can. There's a nice picture, which is unfortunately now covered. I'll probably have to re-record it then. The point is that there are 4 coefficients in the wave functions, 2 from the left and 2 from the right, right going, left going. And just like when you do optics, you have to decide on what it is that you're trying to compute, right? So if you have a mirror and there's a person looking at the image from one side, not the mirror, a semi-penetrable mirror, some kind of a surface through which the light is going to pass. And the person is sitting on one side of the mirror, and the other person from the other side is shining light. So what you know is that since the person on the side that's observing things, he's not shining anything on the mirror, light is only going to move one way on that side. And that means one of the coefficients vanishes. Whereas on the side where you do have a flashlight, light is going to move one way, and then part of it is going to go through, and part of it is going to bounce. And that means that the physical sort of a situation is where you have the freedom to set some of these coefficients to 0 by hand, essentially. But, okay, since the picture has disappeared, I will replace these slides next time. The important sort of connection back to optics is the transmission and reflection coefficients, optics and really electricity and magnetism. And in this quantum solution, you get the amplitudes, which need to be squared to compute the reflection coefficient and the transmission coefficient. Anyway, so finally, we get to the stuff that we didn't cover last time. And the example here is an example of dynamics where you take a problem that you've solved and imagine that you put the wave function, put the particle in the ground state of that problem. So for the square well, or for the infinite well, it would be just the ground state is this guy. And then you disturb the problem. And for various historical reasons, if the problem started in the ground state, and if you change the Hamiltonian, that's called a quench, because it's called a quantum quench. And I'll try to find good historical perspectives on this, why it's called a quantum quench, and I think it's just a name. But anyway, so in this case, what we're going to do is we're going to start with taking the right wall and instantaneously moving it. Imagine that there's a piston, and we're just going to move it by this amount, so that just the size of the well doubles. Now, what you know is that the state, because the wave function used to be 0 here, like this used to be just forbidden zone, but now it's kind of like a vacuum. There's no particle here, not even 0%. I mean, it's 0% chance of finding a particle here initially. And that's not an eigenstate. And that means that basically tells you that the problem is going to have dynamics now. It's going to start sloshing back and forth. Again, the steps are standard. This is what we have seen. So now basically what we have to do is we have to take the information that's there in the time-independent Schrodinger equation and use it to compute things with the time-dependent Schrodinger equation, for which the answer is here. It's always the same answer. Psi of t is a sum over the eigenstates an 5n of x minus en t over h bar. And the information that comes from the time independent Schrodinger equation, of course, is 5n and e of n. But now the new extra information that comes from this quench are these amplitudes an. And the amplitudes need to be computed, and that's basically the only new computation that we have to do in this problem. So the new spectrum is here. All I did was go in, and everywhere I saw A previously, I made it 2A. That's fine. It's easy to do. Right, so here's a new spectrum again. I obtained by doubling. The other thing I did was I moved the origin from the middle of the well to the leftmost corner of it, and that makes all of these cosines can be just written as sines. I think I already mentioned that before. And so finally, the integrals we have to compute are these overlaps between, whoops, this is wrong. Let me just correct that. Between phi of n and the initial state psi, right? Okay, here's the integral. Here's the psi naught, which was just lifted from before, and this is 5n in the new well, and you can see that the biggest difference is that there's an extra factor of 2 here and here, and that's because the well is now twice as big. All right, there's standard ways of doing this integral. Sorry, let me just go back to the PowerPoint. Right, there are standard ways of doing this integral. You basically want to reduce the integrals you want to make them dimensionless. You want to reduce them to integrals from 0 to 1, and that's what I've done here. You can do it trivially by using various trig identities. I didn't trust myself not to make factor of 2 mistakes, so I just went to mathematic and I punched it in. So that's an interesting formula. This is it. This is the formula. That formula has interesting properties. You see that there's a sign at the top, and that sign vanishes for certain n's. They turn out to be even n's with the exception of 2. Okay, 4, 6, 8, all of these vanish. So that's an interesting pattern to note. 1 is finite, only odd ones are finite. Now to see why 2, and we're going to visualize this integral in the next slide, so I'm just going to explain it without that help by what happens at 2. At 2, you're dividing 0 by 0. You're not allowed to do that, right? So you should not trust this formula for 2. Mathematically, you can imagine that n is a parameter which is not an integer, and then you would expect all these things to be continuous, and you can expand near 2 by treating n as a real number and get 1 over 2. Alternately, you can go back to the integral and set n equals 2 here, and there's nothing funny about this integral. It becomes an integral of sine squared. An integral of sine squared is 1/2. Right? That's another way to get this a2. Right? But the formula is very nice because it allows you to just, as long as you know how to avoid 0 by 0, you're always better off using, general formula. Okay. Anyway, so there are interesting facts here. Here it is again. So the fact that all odd ones beyond 4 vanish is cool, and that has to do with the states looking like this. Sorry, I had a picture. I don't know what happened to it. Let me try to draw it freehand. Something happened. Okay, so the picture I wanted to draw, I think it got advanced somehow, is that the initial state looked like this. The new states, they look like, that's the first one, that's the second one. And now if you try to multiply the blue and a red trace and integrate, well, obviously that's going to be okay. But now let's see what happens when you go up and pick another state, which looks like, right? So now let me just label things. The red guy is psi of 0. That's what you start with. And the integral you're trying to compute is the integral in these things and psi of n. Right. Because psi of 0 vanishes here, this integral is basically reduced to the integral here. And now you see you're back to computing overlaps between different functions on the space of the original problem. And you can see that this one, which is psi phi of 1 of the new problem, is not an eigenstate of the original problem because it doesn't vanish at the edge. And so this integral will be just some number. The next one, which is this one, is actually the eigenstate phi 1 of the old problem, right? And that's basically what psi 0 was to begin with. So that integral has to be 1 up to normalization. That's how we got 1 over root 2. Should go back. But now you can see the green guy is some higher eigenstate. Let's count it. 1, 2, 3, 4. It's phi 4 of the old problem. And that means that the overlap between the ground state and the fourth eigenstate of the old problem, it has to be 0. And so that's behind this sort of a pattern of zeros that you found before. Anyway, just to finish this up, because of this interesting pattern, you can separate higher order contributions like so. And the first two are here. Okay. And with this information, you should be able to finish the home. All right. That's it. See you on Monday.